Okay, so let's get to the second part of chapter 6 under normal distribution. So next thing is about central limit theorem. So the central limit theorem states, given that the random variable x has distribution, which may or may not be a normal, with mean mu and a standard deviation sigma, and samples all of the same size n are randomly selected from a population of x values. And conclusions: the distribution of sample mean x bar will, as the sample size increases, approach a normal distribution. The mean of a sample means would be the population mean mu. The standard deviation of the sample means will approach sigma over square root n. So the essence of central limit theorem is we take the whole bunch of samples and we compute the sample mean. And the mean of a sample mean will be the same as the population mean. And the standard deviation of the sample means will approach sigma over square root n. So that's the essence of the central limit theorem. So practical rules commonly used in statistics. First one is for samples of size n larger than 30, the distribution of the sample means could be approximated reasonably well by a normal distribution. The approximation gets better as the sample size n becomes larger. So the larger the sample size, the better the approximation is. So if the original population is itself normally distributed, then the sample means will be normally distributed for any sample size n. So if either one of these is true, then central limit theorem applies here. So the mean of the sample mean, which is mu x bar equals the mean of the is equals to population mean mu. The standard deviation of the sample mean will be sigma of x bar equals sigma over square root n. So this is example from the distribution of 200 digits from Social Security numbers. So this is our distribution. So it's approximately normally distributed. Distribution of 50 sample means for 50 students. You can see it's approximately normally distributed, right? We can fit in a bell-shaped curve in there. So as the sample size increases, the sampling distribution of sample means approaches a normal distribution. So let's take a look at an example, right? Given a population of man has normally distributed weights with a mean of 172 pounds and a standard deviation of 29 pounds. If one man is randomly selected, find the probability that his weight is greater than 167 pounds. B. If 12 different men are randomly selected, find the probability that their mean weight is greater than 167 pounds. So this is how we solve this. The first one is given we're solving for A. Given the population mean of man has normally distributed weights with mean of 172 pounds, standard deviation of 29 pounds. If one man is randomly selected, find the probability that his weight is greater than 167 pounds. So z-score equals x minus mu over sigma, right? Because it's one man, so we still apply the regular normal distribution. So it's 167 minus 172 divided by 29. So the answer, when we run it, is approximately equals to negative 0.17. So looking for the area to the right hand side of 167 pounds. So we're gonna do we're going to the table, look for the area on the left, which is 0.4325. Then we use 1 total area 1, subtract that, give us 0.5675. So 56.75% of man, his weight is greater than 167 pounds. Alright, so this is regular normal distribution. The next thing, let's take a look at the second part, which is B part. Given a population, mean has normally distributed weights with a mean of 172 pounds and standard deviation of 29 pounds. If 12 different men are randomly selected, find the probability that their mean weight is greater than 167 pounds. So here we select a sample of 12 men. And we know that population is normally distributed. Then the sample is automatically normally distributed. Sample of a sample means will be automatically normally distributed. So so using z-score equals to x minus mu over sigma over square root of n. So we have a mean for the sample means is 172. It's the same thing as population mean. Standard deviation of the sample will be equals sigma over square root m, which is 29 over square root 12, which is 8.37158. So based on these, x bar minus mu over sigma equals 167 minus 172 dividing by 8.37158. So we end up with negative 0.60. So so the area to the left hand side of this negative 0.60 is 0.2743, and so the area to the right hand side is 0.7257, right? So that we got it. So the conclusion is 0.7257, so 72.57%. Let's take a look at another example. Okay, so the conclusion for this is given a population of men has normally distributed weights with mean of 172 pounds and standard deviation of 29 pounds. If one man is randomly selected, find the probability of his weight is greater than 167 pounds. His probability for x is greater than 167 equals to 0.5675. If 12 different men are randomly selected, their mean weight is greater than 167 pounds. So which is probability of x bar is greater than 167 is equals to 0.7257. And it's much easier for individual to deviate from the mean than it is for a group of 12 deviate from the mean.